Hey everyone, welcome back, and today let's solve Leetcode problem 1671 titled Minimum Number of Removals to Make Mountain Array. So you may recall that an array is a mountain array if and only if the length of the array is greater than or equal to 3 and there exists some indexed I that is 0 indexed, with I being greater than 0 and less than the length of the array minus 1, such that from array to 0 to array to 1 up until array to I minus 1 up until array to I, array at I is greater than all of these elements to the left of it, and array at I is greater than all of the elements to the right of it, from array at I plus 1 until array at I, or rather array at length of array minus 1. So we're given an integer array nums, and we need to return the minimum number of elements to remove to make nums a mountain array. And if that isn't already obvious, this minimum number of elements already tells us kind of, or hints us rather, that this is probably going to be a dynamic programming problem. So in example 1, we have the input array nums to be 1, 3, 1, and we'd output 0. Why is that? Because the array itself is already a mountain array, so we don't actually have to remove any elements to further make it a mountain array. It already is a mountain array. Why? Because 3 in the middle index is greater than 1, which is all the elements to the left of it, and greater than 1, which is all the elements to the right of it. And so this already is a mountain array, so we don't need to make any insertions or deletions rather. In example 2, we have the input array nums to be the following, and we'd output 3. Why? Because one solution is to remove the elements at indices 0, 1, and 5, so 2, 1, and 2, and that would make it 1, 5, 6, 3, 1, which is going to be a mountain array because 1 and 5 is less than 6, all the elements to the left of it, and 3 and 1 is also less than 6, all the elements to the right of it. Okay, so with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so how can we efficiently solve this problem? Let's kind of break this problem down, like we do for dynamic programming, into smaller sub-problems or subtasks that we have to kind of do. Okay, first, what do we have to do first? We have to calculate the longest increasing subsequence, or the LIS, from the left of the index, and that's going to give us the longest increasing subsequence that ends at each position or index in our input array nums. Then we need to calculate the longest increasing subsequence from the right, and that's going to give us the longest decreasing subsequence that starts at each index. And using those results from the two LIS calculations, we need to use those to identify the longest valid mountain array at any index in our input array nums. Okay, so once we do that, we have to finally calculate the minimum elements to remove by subtracting the length of the longest mountain array from the total length of our input array nums. Okay, so with that out of the way, let's just go ahead and dive straight into the code here. I'm just going to quickly say n is equal to the length of the numbers, because we're going to access the length of our input array nums quite a few times, and so storing that value, or rather length integer, into an input, or rather variable n, is going to be a lot easier to access and operate with. Okay, so once we do that, now I'll actually initialize our left array. It's going to be initialized to just 1 times n, again, where n is the length of the input array nums, and each element is initially set to 1. Why? Because the minimum length of any increasing subsequence that ends at any position is at least 1, right? It's going to be the element itself. Okay, now let's loop through all the elements from 1 to n. So we'll say for I in the range of 1 to n, where again, keep in mind n is the length of our input array nums, right? Because of course the first element itself is an increasing sequence of length 1. Okay, once we do that, we'll have a nested loop. So for j in the range of up until I, our standard longest increasing subsequence format, right? We have to loop over all the previous elements from index 0 till I minus 1 to help us compare each previous element with the current element, okay? So for j in the range up until index I, we have to check if nums at I, again, similar to longest increasing subsequence, problem 300 on Leetcode, if nums at I is greater than nums at j. If the current element, nums at I, is greater than the previous element that we're checking right now in this iteration, nums at j, we can extend the longest increasing subsequence at this element. How do we do that? We set left at I to be equal, of course, to the maximum of itself, because we don't want to make it smaller, and extending our left at j. So it's going to be left at j plus 1, because we found one more element to extend this longest increasing subsequence by. nums at I. Okay, so once we do that, now we want to initialize our right array. So I'm going to set right equal to 1 times, again, the length of the input array nums, where again, each element obviously is going to be set to 1 itself, and this array is going to store the longest decreasing sequence that starts from each index. Okay, so again, pretty similar logic to the first left array. So we're going to say for I in the range, and we're actually going to loop backwards in Python. This is kind of weird. It's not too bad. It's going to be n minus 2 up until -1 exclusive or 0 inclusive, and we'll decrement by 1 each time. Okay, so again, we're just looping backward, and we have to start from the second to last element, which is index n minus 2, up until that first element. And again, that's going to help us calculate that decreasing sequence of any index. Okay, so once we do that, now we have to have, again, our nested loop. So for j in the range of n minus 1 up until I, decrementing by 1 again each time. What does this do? We have to loop over all the elements that come after the index I from the index n minus 1 up until I minus 1. Okay? Or rather, I plus 1, exclusive. Sorry. Okay, once we do that, now we have to check. If nums at I, if that current element, if that's greater than nums at j, we have to, again, extend. Okay, so if the current element is greater than the next element, nums at j, to the right of it, we can extend our decreasing sequence. So we want to say right at I, again, is equal to the max of itself, because we don't want to make it smaller. And we have to extend right at j. So we'll say right at I and right at j plus 1. Because again, we're adding one more element to that current decreasing subsequence, and we want to get the max of these two values to actually track the longest decreasing subsequence that starts from that index I. So once we do that, we're kind of done with the main chunk of the code here. Now we have to initialize our max mountain, and that's going to be initialized to 0. What does this do? This is simply going to store the length of the longest valid mountain array that we find in our input array nums. Okay, so let's continue to loop over. So we'll say for I in the range from the first element, again, up until n minus 1. So we have to loop over all the elements from the index 1 to n minus 2. Why? Because the peak of a mountain cannot be at that first or last position, or the first to last index. It has to be from index 1 up until the second to last element, n minus 2. Okay, so now we have to check. Oops, sorry. If left at I, again, this is kind of the main chunk of our code here. If left at I is greater than 1, and right at I is also greater than 1. Why is this necessary? Why do we have to check if both left at I and right at I are greater than 1? That makes sure that the element at index I can actually act as a peak with valid increasing and decreasing subsequences on both sides. So if that's the case, we want to set the max mountain that we've recorded so far to be equal to, of course, its maximum of itself, because again, we don't want to make it smaller. Similar logic to our longest and increasing and decreasing subsequences, max of the max mountain itself, and left at I plus right at I minus 1. That's the important part here. Okay, so we have to update max mountain to be the maximum of its current value and the total length of the position, or rather of the mountain at this position, which we can calculate using left at I plus right at I minus 1. That is the length of the mountain at this position, or index I. Okay, and ultimately, outside of this for loop here, we simply have to return n minus max mountain. We're again, keep in mind, n is going to be the length of the input array nums. And we have to return the minimum number of removals required, which is again going to be the total length of the input array nums minus the length of the longest valid mountain. Right? And that's going to give us, again, the minimum number of removals required to make this a mountain array. So unless I made any syntax errors here, this should be accepted and it should work. It's judging. And as you can see, this is just about as efficient as you can get. Okay, so what does this code overall kind of do? How does it work? How does it operate? What is the use case of it? Okay, so we have to first calculate the longest valid mountain array. First, we have to find the longest increasing subsequence from the both sides. We have to identify the best peak and use the minimum removals formula, n minus max mountain, to determine how many elements to delete to actually get a mountain array at minimum. Okay, so for the time complexity, this is going to be big O of n squared. Why? Because of the nested loops, right? We have nested loops over here And here, technically, we'd have a coefficient, but it doesn't really matter. This would simplify to big O of n squared. And so the space complexity is going to be big O of n. Why? Because we use two additional arrays, left and right, and they're each going to have a size of n, or again, n is the length of the infinite right nums. And so our space complexity is going to also be big O of n, or a linear time memory complexity solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.